Okay, good morning, all of you. So today, once again, we will try to discuss about the few things related to electromagnetic induction. In the previous session, we discussed what is mean by that electromagnetic induction and what is the basic requirement. So the basic requirement of electromagnetic induction is the change in magnetic field. And this change in magnetic field is either the movement or change of a magnet or magnetic field, or the movement or change or rotation of a conductor. In both the cases, according to Faraday's law, the EMF is induced. So the Faraday's gives two laws. The first is related to the basic requirement of an induced EMF, and second is related to the magnitude of an induced EMF. So the Faraday's first law gives that when change in magnetic field linked with the coil or conductor, EMF is induced in that coil or conductor is there. This is the Faraday's first law. And the second law gives that the magnitude of induced EMF in a coil or conductor is the rate of change of flux linkage. What is meant by the flux linkage? The flux linkage is the product of N into phi. Okay, so that's why according to the Faraday's second law, we have that the one mathematical equation for the induced EMF, and that equation is E is equal to N d phi by dt, where d phi by dt is the rate of change of a flux. D phi by dt is the rate of change of flux. When we multiply it with the N, then it becomes the rate of change of flux linkage, because N into phi is the flux linkage. So this is the EMF equation of an induced EMF according to that Faraday's law. But what is its polarity? What is the polarity of an induced EMF, and what is the direction of a current due to this induced EMF? That can be found by using the Lenz's law here. And what the Lenz's law gives that? The Lenz's law gives that the polarity of an induced EMF and hence current is always opposed the cause produced it. So that the Lenz's law is reflected in the equation of induced EMF with a minus sign. So that the final equation for that induced EMF is minus N d phi by dt. So this minus sign is nothing but the Lenz's law. What it indicates? It simply indicates that the polarity of this induced EMF is always opposed the cause produced it, and the main cause is a change in magnetic field. Main cause is a change in a magnetic field is there. And now we will give the more trace on that induced EMF. What is the basic requirement? Once again, the basic requirement to that induced EMF is a change in magnetic flux linked with the coil or conductor. This is the basic requirement. In that, a very important word is a change. Get it, my point? Then this change in magnetic field is either due to the movement of a magnetic field or due to the movement of a conductor. And based on that, the induced EMF can be classified into two types. One is the dynamically induced EMF. When we say that dynamically induced EMF, when conductor, when it is moving, or sorry, not moving, it's a dynamic. And the dynamic is nothing but what? It's a moving or changing. When the conductor is dynamic, it means that the magnetic field is rotating or changing. In that case, the EMF induced in the conductor, we call it a dynamically induced EMF. Statically induced EMF. Second type is what? Statically induced EMF. What is meant by statically induced EMF? In this case, let me take that what is this? I don't know. Here, when I consider that the conductor is stationary, here I can write. Give me 1 minute. When the conductor is stationary, so that time we say that the induced EMF, stationary means fixed, induced EMF is a statically induced EMF. Is it right? Now see that dynamically induced EMF. If you see this diagram, then you will notice the one thing here, the N pole and S pole of the magnet are fixed. It means that the magnetic poles are fixed. It simply gives that the magnetic field is stationary. But within that uniform magnetic field, one rectangular coil is rotated. And when this rectangular coil is rotated, so during their rotation, it curved the magnetic flux. And according to the Faraday's law, when it curved the magnetic flux, definitely EMF is induced in this rectangular coil. And in this case, as the conductor is a dynamic, as the conductor is rotating, so that the induced EMF in this case is known as dynamically induced EMF is there. Try to read it. If conductor is rotating or moving in a uniform magnetic field, it cuts the magnetic lines, and hence according to Faraday's law, an EMF is induced in the conductor. This induced EMF is called dynamically induced EMF is that. Then that example, an example of dynamically induced EMF is a generator. In the generator, the magnetic field is stationary and the coil or conductor is rotating, so that the generator is an example of dynamically induced EMF is there. Now the second type is statically induced EMF. Statically, it gives that conductor is a static, means a stationary. If conductor is stationary, then what is the movable part? What is the changeable part? It's a magnetic field. And now see the definition. If the magnetic field is a changing or moving and conductor is stationary, according to Faraday's law, an EMF is induced. This induced EMF is called statically induced EMF is there. Now, statically induced EMF is also having its two types. What are these two types? One is a self-induced EMF and another one is a mutually induced EMF. Now see that one by one, what are the types of the statically induced EMF? But let me clear that the one thing here, these two types, self and mutual induced EMF, are the types of a statically induced EMF. And when I say that it is the type of a statically induced EMF, it means that conductor is stationary. Please keep these things in your mind. Okay. An example of statically induced EMF is a transformer. Later on, we will discuss in detail about the transformer, because this is the part of our chapter is there. Get it my point? But try to remember the thing here. The transformer is a static. It means that it is the conductor of the transformer is a stationary. Then what is the rotating part? It's a magnetic field. That's why the transformer, it works on the principle of statically induced EMF. This is the main point is that this is the example. Now see that self-induced EMF. Now the word is very important. What is that word? Self. It means that when due to the change in current in the own or change in its own current, the magnetic field is a changing, and because of that EMF is induced. This induced EMF is known as a self-induced EMF. Now please try to see here. Let me try to explain that what is meant by the self-induced EMF. Please concentrate very carefully. Then and then you can remember this self-induced EMF and you will try to understand this thing here. Here, whatever that orange color bar is there, we call it a halo cylinder. Have you observed that orange color halo cylinder? On that halo cylinder, a one wire is wound in a n number of turns, and the end of that wire is connected with one battery, one switch, and one variable resistor. This is the experimental arrangement to understand the self-induced. What is that arrangement? One hollow cylinder on which a wire is wound in a n number of turns. End of that wire is connected with the three things. One is a battery, one is a switch, and second one is a potentiometer, or we call it a rheostat or variable resistor, with which we can vary the resistance of that wire. Is it right? Now, just try to concentrate here. When this switch S is closed, what happened? When S is closed, definitely a current it flows through the wire here. When the current it flows through the wire, according to the Oersted experiment, that magnetic field is produced. Is it right? And when I say that here, when S is closed, a current it flows through the wire, and because of that, magnetic field is generated. And what is the shape of that magnetic field? As you observe in the diagram, this is the shape of that magnetic field. As we know that one end of solenoid acts as a north pole, other end of solenoid acts as a south pole, and the magnetic field, it always originates from n pole to the south pole. In this way, we will get the shape of that magnetic field due to this solenoid coil is there. But now, when we try to open that switch, then definitely no current will flow through the wire. Is it right? And when the current it will not flow, so definitely no magnetic field is generated. But now, if we continuously open and close the switch, if you continuously open and close the switch, what happens? When switch is S is closed, definitely certain value of current it flows. If switch is open, definitely current becomes zero. And if you do these things continuously, then continuously the value or the magnitude of current becomes 0 to its maximum value, 0 to maximum, 0 to maximum. It means that a current flowing through this wire or the solenoid is changing continuously. If the current through the solenoid is changing continuously, definitely it will create the change in magnetic field around the solenoid. Do you agree with me? And
Yes, sir.
if the change in magnetic field, when it link with that coil, आता ती change in magnetic field, yes, त्याच coil ला पण link होणार आहे. And what the Faraday's law gives that when the change in magnetic field link with the coil, then EMF is induced in that coil is there. And because of that, in the same coil, EMF is induced, and that induced EMF is called as a self. आता त्याला self का म्हणलंय? का तर त्याच कॉइल मध्ये फ्लो होणारा करंट चेंज होत होता आणि त्याच्यामुळे चेंज इन मॅग्नेटिक फील्ड तयार होत होती आणि त्यामुळे ईएमएफ इंड्यूस होत होता त्याच कॉइल मध्ये. दॅट्स वाय EMF induced in the same coil due to change in its own current is called as a self-induced EMF. Try to read it. The self-induced EMF is the EMF which is produced in the coil due to change in its own flux link with it. If the current of the coil is changed, then the flux link with its own turn will also change, which will produce an EMF that is called as a self-induced EMF. Is it that clear? Yes or no?
Yes, sir.
Okay. And then the second point is the mutual induced EMF. Now see that this is a mutual induced EMF. Now let me try to explain that experiment setup. Now here the two hollow cylinders of orange color are considered. Both the cylinders are wound with a n number of turns of a wire, but Here I consider that this is a solenoid A and this one is a solenoid B. A solenoid A is connected with the battery, switch and the variable resistor, but the solenoid B is simply connected with the galvanometer. म्हणजे A solenoid बॅटरीला कनेक्ट केलेला आहे, परंतु B solenoid हा simply galvanometerला कनेक्ट केलेला आहे. And both these solenoids are placed near to one another. And now in the solenoid A, if switch S is closed, आता इथं तुम्हाला डायग्राम मध्ये दिसेल बघा, एनिमेशन मध्ये दिसेल. When switch S is closed, a current it flows, and when switch S is open, the current becomes zero. And if you are doing these things continuously, the value of current flowing through the coil is changing continuously. And if the current value it goes on changing, definitely due to this change in current, a change in magnetic field is produced by the solenoid coil A. कोण तयार करते change in magnetic field? The coil A तयार करते. But coil B is placed near to coil A. And when the change in magnetic field produced by the coil A, when it is linked with that coil B, then according to Faraday's law, EMF is induced in a coil B. But why this EMF is induced in a coil B? Due to change in current in a coil A. So this induced EMF in a coil B is known as a mutual induced EMF. Why it is called as a mutual? कारण बी कॉइल मध्ये ईएमएफ इंड्यूस होतोय जो कॉइल ए मध्ये चेंज होणाऱ्या करंटमुळे. म्हणजे दुसऱ्या कॉइल मध्ये करंट चेंज झाल्यामुळं जर ईएमएफ इंड्यूस होत असेल तर त्या इंड्यूस्ड ईएमएफ ला आपण काय म्हणणार आहोत? म्युच्युअल इंड्यूस्ड ईएमएफ. मग आता या ठिकाणी कॉइल ए मध्ये पण ईएमएफ इंड्यूस होतोय आणि कॉइल बी मध्ये पण ईएमएफ इंड्यूस होतोय. का तर ए कॉइलनं जी चेंज इन मॅग्नेटिक फील्ड तयार केलेली आहे ती चेंज इन मॅग्नेटिक फील्ड कॉइल ए ला पण लिंक होते आणि कॉइल बी जवळ ठेवल्यामुळे कॉइल बी ला पण लिंक होते. पण कॉइल बी मध्ये जो ईएमएफ इंड्यूस होतो त्याला आपण म्हणणार आहोत म्युच्युअल इंड्यूस्ड ईएमएफ. का म्हणणार आहोत? का तर कॉइल ए मध्ये चेंज होणाऱ्या करंटमुळे कॉइल बी मध्ये ईएमएफ इंड्यूस होत आहे. परंतु कॉइल ए मध्ये जो ईएमएफ इंड्यूस होईल त्याला काय म्हणणार आहोत आपण? सेल्फ इंड्यूस्ड ईएमएफ. दिस इज द डिफरन्स बिटवीन सेल्फ इंड्यूस्ड ईएमएफ and the mutual induced EMF is that. Is it that clear? Get it my point? Okay, so try to read it. Mutually induced EMF occurs in between two coils. Let A and B are the two coils which are placed close to each other. If coil A is joined to a battery, a switch, and a variable resistor R, and coil B is connected to a sensitive galvanometer G. This is the experiment setup. Now, when switch S is closed, a current will flow through the coil A, will produce a magnetic field in which partly link with the coil B. As current through A is changed, a flux linked with B is also changed. According to Faraday's law, induced EMF is produced in the coil B, and this EMF is known as mutual induced EMF. Is it that clear? Self and mutual induced EMF मधला फरक लक्षात आला?
Yes, sir.
Okay. Now, let's take that the next point. Self-inductance. Now, what is meant by the self-inductance? As I already explained. Okay. See that. Suppose I consider here a one coil which is connected with the battery and with one switch. This is a switch. This is a battery. This is a coil. Now consider that S is closed. what happened? When S is closed, definitely current it circulates, current it will flow. Suppose this I having its a certain value, X ampere. Is it right? This is the one case. Now S is open. If S is open, the circuit becomes open, so definitely I becomes 0. This is the case second. Is it right? And now when we continuously doing the open and the close the switch, definitely this I will change continuously. Is it right? When switch S is closed, I becomes X ampere. When switch S is open, I becomes 0 ampere. So 0 to X, it will be continuously changing. And due to change in this current, a change in magnetic field is produced around the length of that conductor or the coil here. This is the shape of that magnetic field. Is it right? And now, when this change in magnetic field, it link with the same coil. That's coil a link honare. Then according to Faraday's law, EMF is induced, and in this case, this induced EMF is called as self-induced EMF. Is it right? So the equation of the self-induced EMF or that induced EMF, which is nothing but E is equal to N d phi by dt. Barabar hai? But what is the direction of this induced EMF in the coil? The direction of an induced EMF in the coil according to Lane's law, which is always opposed to what? A cause produce rate. And what is the cause? The cause is this change in current. कारण हा करंट चेंज झाल्यामुळं मॅग्नेटिक फील्ड चेंज होते. मॅग्नेटिक फील्ड चेंज झाल्यामुळं या कॉइल मध्ये ईएमएफ तयार होतोय. सो दॅट द कॉज इज अ change in current. It means that every coil has a tendency to oppose the change in current through it. लक्षात घ्या. Every coil has a tendency to oppose the change in current through it. This property of a coil is known as a self-inductance. Is it that clear? Is it that clear? Now try to read it. Let me try to show that the definition. The property of a coil which opposes any change in the amount of a current flowing through it is known as a self-inductance, or simply it can be also known as an inductance. Simply inductance, and it is represented with a capital L. So what is meant by the self-inductance? The property of a coil which opposes any change in amount of current flowing through it is called as a self-inductance. Now, it is denoted with a capital L and its a unit is Henry. Okay. Now see that what is that expression of that self-inductance is that. So this is the diagram. As you know that with this diagram, I have already explained that what is meant by the self-induced EMF. And right now I have explained that what is meant by the self-inductance. And now we are trying to derive the formula for self-inductance is that. Consider the coil of N turns carrying a current of I ampere. If the current in the coil changes, the flux link with the coil is also changes. This will produce the self-induced EMF, which is given by that equation E is equal to N d phi by dt. This is that equation according to the Faraday's second law. Now, this change in a flux is due to the change in current. So that, can I write it down? E is equal to N d phi by dt is directly proportional to di by dt. What is meant by this di by dt? What is this?
Charge.
It is nothing but rate
Rate of change current.
change of करंट. आता मी ह्याला इथं इक्वेशन असं का लिहिलं, E is equal to N d∅ by dt. हे इक्वेशन तर आपल्याला माहित आहे, but which is directly proportional to di by dt. Why I have written like that? Because what is the main cause to induce the EMF? त्या कॉइल मधून चेंज होणारा करंट, फ्लो होणारा करंट म्हणणार नाही मी इथं, कारण करंट हा कंटिन्युअसली चेंज होतोय 0 to x एम्पियर, 0 to x एम्पियर, like that. Get it my point? So the induced EMF is actually directly proportional to the di by dt. That's why I have written that equation E is equal to N d∅ by dt is directly proportional to di by dt is there. So I can also write it down. E is a directly proportional, induced EMF is a directly proportional to rate of change of current. And now when I want to replace this proportional sign, we can replace this proportional sign with a proportional constant, and this proportional constant is nothing but self-inductance. It can be denoted by L, capital L. This is the self-inductance here. Get it my point? So this is the another one equation now you observe here. So the first equation is E is equal to N d∅ by dt and E is equal to L di by dt. आता या ठिकाणी मुलं कन्फ्यूज होतात असा माझा एक्सपिरियन्स आहे बघा. तर कन्फ्यूज व्हायची गरज नाहीये. According to the Faraday's second law, our equation for induced EMF is N असेल तर त्याला मल्टिप्लिकेशन फॅक्टर काय असला पाहिजे, फाय असला पाहिजे, कारण N फाय फ्लक्स लिंकेज, हा कन्सेप्ट लक्षात ठेवा, फ्लक्स लिंकेज. बरोबर आहे. म्हणजे N असेल तर त्या ठिकाणी di बाय dt येणार नाही, तिथं d∅ बाय dtच येणार. आणि ज्यावेळेस L असेल, सेल्फ इंडक्टन्स. व्हॉट इज द सेल्फ इंडक्टन्स प्रॉपर्टी लक्षात ठेवा. काय प्रॉपर्टी सेल्फ इंडक्टन्सची? इट ऑलवेज अपोज द चेंज इन करंट थ्रू इट, सो दॅट L इज इक्वल टू di बाय dt. जर थोडस कन्सेप्च्युअली लक्षात ठेवलं तर या दोन इक्वेशन मध्ये कधीच कन्फ्यूज होणार नाही. पण जर तुम्ही व्यवस्थित केअरफुली जर ते दोन इक्वेशन बघितले नाही तर डेफिनेटली यू विल बी कन्फ्युज्ड. And now here the second equation for that induced EMF, we got it here. Let's we try to derive the few more equations about the self inductance. Now here this L is nothing but the self inductance. Please try to remember these things here. Okay, now let's we try to derive the equations for the self inductance. See that as we know that this is the first equation for the self inductance, E is equal to L di by dt. Di by dt, it stands for rate of change of current, but L is the constant. L is the property of a coil and it is always constant. That's why it is taken outside of the derivation here. And the derivation is what? Changeable parameter is what? It's a current. So that I can also write here, if I want to derive the equations for the self inductance, so I can write L is equal to di by dt. If I transfer to left hand side, so it becomes L is equal to E divided by di by dt. This is the first equation for the self inductance is that. Simple. Okay. Now let's we try to derive one more equation for the self inductance is there. How you can derive that one more equation? Just see here. As you know that the general formula for the self induced EMF, which is equal to N d∅ by dt. आता बघा इथे N आलाय. So according to this equation, can I write like that? D dt of N phi. But out of that, the constant term is a N. So that I can write like that also. These two equations are nothing but the same. Get it my point? Okay. And now according to this equation, can I write that E is equal to L di by dt? This is that equation. Out of that, L is the constant, just like a N. So I can write E is equal to d dt of Li. बघा आता हे दोन इक्वेशन्स बघा. E is equal to d dt of n phi and E is equal to d dt of Li. So can I equate these two terms, Li and n phi? Of course, yes, because induced EMF, the equation is same. Induced EMF, if it is same, then I can equate these two terms. Li is equal to n phi. So that I can write L is equal to, because आपल्याला काय पाहिजे, L चे expressions पाहिजे. So I can write L is equal to n phi by I. This is the second form of induced EMF is there. लक्षात येत आहे? Yes or no? Hello? Is it that clear?
Yes, sir.
Okay. Now this is the second equation. आता या सेकंड इक्वेशन मध्ये व्यवस्थित ऑब्झर्व करा. सेकंड इक्वेशनला काय आहे बघा, L is equal to n phi upon I. बरोबर आहे. आता त्यापैकी n काय इंडिकेट करतोय हो? What that n indicates?
Number of turns of coil.
मग ते कॉन्स्टंट आहे का व्हेरिएबल आहे?
Constant.
Okay. What the phi? It's a flux link with that number of turns. What the I is the current flowing through the number of turns. मग आता या तीन पॅरामीटर n, phi आणि I, या तीन पॅरामीटर पैकी जर व्यवस्थित बघितलं तर तुम्हाला n हा कॉन्स्टंट असेल आणि ज्या प्रकारे I चेंज होईल त्या प्रकारे तुमचा phi चेंज होणार. म्हणजे व्हेरिएबल टर्म्स हा phi आणि I. आता जर मला त्याला डिफरन्शियल फॉर्मच्या फॉर्म मध्ये लिहायचं असेल, डिफरन्शियल फॉर्मच्या इक्वेशन मध्ये लिहायचं असेल, तर मी त्याला असं लिहू शकतो का बघा, L इज इक्वल टू n d phi by di. Can I write like that?
Yes, sir.
Of course, yes, because n is the constant term. Is it right? बघा आता इक्वेशन हे वेगवेगळे यायला चालू झालेले आहेत, त्यामुळे तुम्ही थोडंसं ऑब्झर्व करा, केअरफुली ऑब्झर्व करा आणि ते अंडरस्टँड करून घ्या. Get it my point? And now based on that formula, L is equal, second formula, we will try to derive one more expression for the self inductance is there. आता ते कसं derive करायचं? Just see here. From the value of self expression, आपल्याला माहित आहे what is that second equation. आता तो सेकंड फॉर्म जो बघितला तुम्ही, तर तो कोणता आहे? n phi by I. मी तोच घेतलेला आहे इथं. मग त्याच्यावरून आपण काय लिहू शकतो डिफरन्शियल फॉर्म मध्ये? L is equal to n d phi by di. आता याला इक्वेशन नंबर A म्हणा. Get it my point? And now according to our basic equation of a magnetic circuit, कोणतं म्हणतो, कोणत्या इक्वेशनला आपण बेसिक इक्वेशन म्हणतो सांगा बरं? Which equation in the magnetic circuit we call it's a basic equation? Yes, please. So this is nothing but phi is equal to mmf upon reluctance. This is our basic equation. Get it my point? आता तुम्ही या इक्वेशन A मध्ये बघा d phi by di आहे. मग आता या आपलं जे काय बेसिक इक्वेशन आहे phi is equal to mmf upon reluctance, जर मी दोन्ही साइडला if I try to take the derivation of both the side with respect to I, so what is the derivation? d phi by di is equal to right hand side ला काय उरेल हो सांगा?
L by
हा, yes please, correct. सांगा अजून एकदा.
L divided by n is equal to d phi by di.
It's a n upon s. It remains because if I want this ratio d phi by di, I can try to differentiate with respect to I to the both side, and here we got d phi by di is equal to n by s. d phi by di is equal to n by s. मग आता जर मी ही d phi by di ची n by s व्हॅल्यू जर इक्वेशन A मध्ये ठेवली, equation A becomes what I get? L is equal to n into n by s. So can I write down here L is equal to n square by s? This is the third form of a self inductance is there. Is it that clear? मग आता किती इक्वेशन्स आपण आतापर्यंत बघितले बघा. बघा आता पहिलं जे इक्वेशन्स बघितलं, व्हॉट दॅट इक्वेशन? E is equal to N d∅ by dt. हे पहिले इक्वेशन बघितलं अकॉर्डिंग टू फॅराडेज लॉ. आता दुसरं इक्वेशन सेल्फ इंडक्टन्स वरून बघितलं. कोणतं बघितलं? E is equal to N di by dt. बरोबर आहे. तिसरं इक्वेशन, चौथं इक्वेशन आणि पाचवं इक्वेशन हे सेल्फ इंडक्टन्सच्या बाबतीमध्ये बघितलं, एलच्या बाबतीमध्ये बघितलं. पहिलं इक्वेशन काय बघितलं? एल इज इक्वल टू ई डिवायडेड बाय डी आय बाय डी टी, फर्स्ट इक्वेशन. दुसरं इक्वेशन काय बघितलं? एल इज इक्वल टू एन फाय अपॉन आय, किंवा यालाच मी असं पण म्हणू शकत होतो, एन इज इक्वल टू डी फाय बाय डी आय. बरोबर आहे. आणि पाचवं इक्वेशन आता आपण बघितलं, एल इज इक्वल टू एन स्क्वेअर बाय एस. इज इट दॅट क्लिअर? Yes or no?
Yes.
Okay, so today what you have to do, whatever these equations we studied, you have to go in a details once again. If still confusion is there, again once again you have to go and study that same part till your confusion will be zero. And then you will observe that once you will clearly understood this concept, then after that it's not necessary to study the same part here. And this is the right time to study this thing is there. Is it that clear? Okay. And now let me try to explain one more thing here. Give me 1 minute. Let me try to explain one more thing. Now, all of you please concentrate here. Suppose, now here, once again, we consider that a one coil. Suppose this is a one coil. Okay. Let me assume that this is a coil A. Number of turns of a coil A is a LA, and this coil is connected with a battery with one switch S, and here I say the battery. आता मला सांगा, ज्यावेळेस S हा क्लोज होईल, काय होईल? Please contribute in the discussion. When
Current.
S is closed, definitely current it flows. So if I consider that a certain value of current it flows. Now, due to this current, can I say that magnetic field is produced? Yes or no?
Yes, sir.
Okay, magnetic field is produced, and the shape of that magnetic field is this way. Okay, this is the shape of that magnetic field. Now, I say that this is a case first, and now I say that switch is open. What happened? I becomes 0, and this is a case second. And if we are doing continuously, I say that due to change in current, the magnetic field produced is also changing. Is it right? We already discussed this thing. And now, if you assume that another one coil B, which is placed near to the coil A. Suppose I say that, sorry, this is NA. The number of turns of a coil B is a NB. बरोबर आहे. मग आता ही कॉइल B कॉइल A च्या जवळ प्लेस केलेली आहे. काय होईल? काय होईल? या कॉइलची चेंज इन मॅग्नेटिक फील्ड कॉइल बी ला लिंक होईल का? येस ऑर नो?
येस सर.
बरोबर ना, कारण कॉइल बी आपण ए च्या जवळ ठेवली आहे. मग जर कॉइल बी ए च्या जवळ ठेवली आहे तर कॉइल ए ची चेंज इन मॅग्नेटिक फील्ड कॉइल बी ला पण लिंक होईल. बरोबर आहे. मग आता जर कॉइल बी ला चेंज इन मॅग्नेटिक फील्ड लिंक झाली तर काय होईल?
EMF induced.
According to the Faraday's law, EMF is induced. Is it right? And if the EMF is induced in this coil B, what is its type? कसल्या प्रकारचा induced EMF म्हणतो आपण याला? It's a mutual induced EMF. And now, can I write what is our basic formula for induced EMF? E is equal to N d phi by dt. आता इकडे लक्ष द्या बघा, हे इक्वेशन फार महत्वाचं आहे. हे d phi by dt म्हणजे रेट ऑफ चेंज ऑफ फ्लक्स. हे कशाला लिंक झालंय? N ला लिंक झालंय. आता बघा, कॉइल बी चा नंबर ऑफ टर्न्स किती आहेत? NB कन्सिडर केले. आता मी इथं म्हणतो EMF induced in a coil B is a mutual induced EMF, so it can be denoted by E to the base M. M stands for mutual. मग कोणत्या कॉइल मध्ये जनरेट झालेला EMF ला आपण म्युच्युअल इंड्युस्ड EMF म्हणतोय, तर ते कॉइल बी मला. कॉइल बी मध्ये इंड्यूस झालेल्या EMF ला आपण म्युच्युअल इंड्युस्ड EMF म्हणतोय. मग आता सांगा मला, कॉइल बी च्या किती नंबर ऑफ टर्न्स आहेत आणि त्याला कोणता फ्लक्स लिंक झालेला आहे? तर यानुसार बेसिक इक्वेशन नुसार जर मला इंड्युस्ड EMF चा म्युच्युअल इंड्युस्ड EMF चा जर इक्वेशन लिहायचं असेल, सो कॅन आय राईट इट डाउन, विच इज इक्वल टू NB इज द नंबर ऑफ टर्न्स ऑफ अ कॉइल बी. आणि कोणता फ्लक्स लिंक झालाय? तर कॉइल ए न तयार केलेला फ्लक्स लिंक झालाय. सो कॅन आय राईट इट डाउन हियर, d phi A by dt. Do you agree with this equation? Yes or no?
Yes, sir.
So this is the equation of mutual induced EMF. Get it my point? And now I can say that here d phi A upon dt is the rate of change of a flux produced by coil A. And this rate of change of flux produced by coil A link with a coil B. In that, NB is the constant term. So can I write the same equation, e to the base m, which is equal to d dt of n to the base b into phi A. Do you agree with this equation? Please check it. Yes or no? Hello?
Yes, sir.
Okay, so today we stop here. And now, today once again we will discuss the few more equations about the mutual induced EMF. But till then, it's my request to all the students, what the concepts we discuss in this session also and in the previous session also, please read it very carefully. Then you will enjoy the next session. Otherwise, it's a quite confusing thing is there. Please take a note of these things. Okay. So today we stop.